Ooh, cool. Let's see if this works. Your channel. Watermark on, blah, blah. Oh, it's working. That's cool. Just gonna get the quality up. Oh, it's working. That's cool. I'm just staring at myself. Just gonna get the quality up. Oh, it's working. Okay. Where's that link? To Ooh. Alright, what fork are we on? Branch. Alright, curvature factor learner, steer actuator delay, heat. You want to test something? I'm debating if I should release. All right, so let's take a look at stock open pilot devel. So if we take a look at close. We take a look at we'll look at path planner and we'll look at interface. So within interface there is something called steer actuator delay, and steer actuator delay is it's really a fudge factor is what it is. So if you take a look at what steer actuator delay does, the current state is crammed into this function, and basically it takes x is the speed, psi I believe is the yaw error, could be wrong there, but it divides it by the delay since it is a multiplier. So let's say our speed is 13 meters a second times the standard steer actuator delay value is 0.12. The speed that is shoved into the MPC for calculation is 1.56 meters a second for speed, and then for PSI it's the same deal. So the general guidance on steer actuator delay is that it's supposed to be set to the torque response of the EPS actuator, electric power steering actuator. And take a look at some of the code comments. 0.2 in seconds, so that'd be 200 milliseconds. And then you have, that'd be, so the default delay isn't even consistent among the interface files. So Honda is 0.1, 0.1 Honda, which is the gold standard per se, is 0.1. And then default delay for Toyota is 0.12. So it might just be the, so it's not really, it's like a steer delay. It's like this value can, anyway, it's a fudge factor. I hate this factor. I hate this value because when you look at MPC, if your MPC can't handle actual inputs, then there's something wrong with your MPC. Excuse me. So what we're going to do, we're going to revert that, which removes the steer actuator delay completely. Done. Pull from dwell, curvature. All right, so we're going to take a little detour and merge. Merge PR. Streamer mode is enabled. What is streamer mode? I don't even know how to turn it back on again. Anyway. Streamer mode. Could hide sensitive or personal information. Huh, oh, that's cool. Notification sounds. Minimizes Discord tags. Huh. That's great. All right, so I should just reset to this commit, but the problem with doing that is going to break people's git trees, and since people are actually using this, I'm not going to do a git reset. So I went ahead and rewrote the learner to be its own module earlier. I don't know if I can make this any bigger. Nope. But because I made it a module, I was able to separate my code out with Path Planner itself. So what I really want to do is, you see this delta desired right here. So in normal MPC solutions, you usually fit in the actual delta, which is the steering angle of, I believe the steering angle of, let's take a look at Apollo actually. We'll take a look at modules, planning, and tuning, auto tuning. Cool, MPC controller. So they have their own MPC controller H, lat controller. We'll take a look at the lat controller as well. Lat longitudinal, lateral. We don't need the test. MPC controller. This is MPC controller.h. Compute a steering target throttle brake based on current vehicle status and target trajectory. MPC lat. Okay, let's take a look at lat. Egen, yeah. So we have LQR. There is no QR here. Got some sort of login going on. Now they got lateral error, heading error rate. Curvature. That's funny. Looks like we got a feed forward as well. Steering position. All right. Rate contribution. I don't know what rate contribution is. So it looks like they're using no QR. Give vehicle parameters. Okay, so they got wheelbase, steer ratio, the maximum amount of degrees that it can turn, and that looks like this is in radians. Low speed bound. Max acceleration. So that's likely degrees per second constraint within the LQR controller. We got wheelbase. Oh, we have moment of inertia. Okay. LQR IPS control configuration. We got max iterations of the MPC controller, I believe. Minimum speed protection. Okay, so there's our equations of motion. That controller matrices. there's the vehicle model right there. It's all in C though, but lateral gain scheduler. Holy crap. So this is reverse. So they got a vehicle model for reversed. That's the lateral acceleration. Steer limitations of the current speed. So I bet that's how much the steering wheel can move based on speed, like some sort of lookup table. Got feed forward. Holy crap. Some jerk down here. Hey, it looks like let's see, control time interval, corner stiffness, front and rear. You got wheelbase, mass, distance from front to center, yeah, rotational inertia. You got your steer ratio, maximum turn. So there's your control horizon. They're only using 10. While the control horizon for OpenPilot is 50, which is insane. Feed forward. Cool. NPC controller, NPC controller, NPC controller. There we go. Here is the actual NPC controller. So instead of using something like Ocado off the hop, they just decided to use to write their own. I mean, they even have their own copyright header up here. Let's see what kind of work they've done on it. So it's rather active. You take a look at Comma's NPC controller, and it has a vast majority of the commits are 2 years ago with very, very minor updates. Digital filter, lateral error filter, filter. That's a little pass filter. Okay. Expand the model to accommodate more combined states. Yes. Steer weight interp, heading error interp, gain scheduler. Using OSQP Q poses. That's pretty cool. Anyway, this is how you write a real. This is how you write a real NPC. Now, since they're using a Kato toolkit, they can vastly simplify the amount of code required, and it will actually generate it'll generate everything for them. So it's an automatic initialization as well. Boop. So anyway, anyway, what am I babbling on about? Oh, long story short, so you would think that the NPC would want to know where the steering wheel is when it tries to come up with its path planning, but actually, due to whatever reason, the actual last steering angle, the actual last steering angle is actually piped in, the last generated angle, the desired NPC. So, if you have a planer that's running 100 times a second and you're trying to minimize error subject to constraints, it doesn't do much good when you feed in the lane lines and the depoly and the curvature factor, and then you tell it the steering wheel immediately is exactly where it wants it to be every single time. They say they like using NPC as a kinematic angle generator, but I think that the NPC solution in OpenPilot just isn't very robust or planned out. I mean, it works, but at the same time, Apollo only supports basically the linking MKZ, so you can have a full vehicle model and actually take a look at, oh, if your if the car weighs this much and the wheelbase is this much and so forth, and you're turning, this is how much the wheels are. This is how much the wheels are going to slip. So. So we are, what did I say about tuning? Where's tuning at? Alright, so current state delta stereo cost 0.1. So let's go back to here and okay, we will go back to, let's see, this is the enhanced centering. We will leave that out. We'll go back to here, get reset. Oh, Jesus. How do I pause the live stream? Let's see. Oh, well, that's cool. Okay. Oh, that's right. Microsoft owns GitHub now. So that's why that little dialog came up for login. Alright, so we reverted to removing the steer actuator delay. Okay, let's make sure everything's right. So 2255 greater than absolute. Okay. Linear rate 6,000. Oh, it automatically added the personal access token and everything. Let's see, what are we doing here? We want to change that. Current state delta. Vehicle model dot steer ratio. So that should be CP steer rate cost. So that's car parameters. AP steer ratio, excuse me, find vm.sr. So that's all just in Path Planner. So we'll go into Path Planner, and we will we equals CP steer ratio. Okay. Alright, CP is passed in there. So find and replace vehicle model dot steer ratio, and we'll place that with car parameters steer ratio. Boom. Normal vehicle model for that. What'll be stiffness factor? One match. Vehicle model update params. Let's see VM dot. So we're still using the vehicle model for the curvature factor, which is okay. That's fine. There's a speed base interp in there. Alright, change my mind. I'm not refactoring right now, I'm just doing other stuff. So current state, push. Alright, we'll take a look at interface. And this is set up for INDI right now. So let's go ahead and set this up for PID control. And we'll use some TSS2 configs. Let's default TSS2. We'll go ahead and do some speed-based tuning in there while we're at it. So 30 miles an hour, 2 meters per second is 13.4112. And then we'll go up to 80 miles an hour, 35. Copy this array. Well, we don't really need to interp. We don't really need to interp that. So we'll do 0.4 at low speeds, and we'll kick it up to 0.6 at high speeds. We'll keep KP the same. We'll keep KF the same as well. Full torque at 10 degrees. Okay, that's fine. See, we're running without a steer actuator delay because I removed it because I don't like inexplicable hacks. What's our cost? Stereo cost is still 1 dot. So let's move that to here. Then we will redefine that there. Actually, let's see what other people are going to feel, because everyone else is going to be running at 1.0. Okay, is my 15 degrees a second steer rate constraint in here? So that's, what's this? Previous PID. And lateral MPC generator. Take a look at the subject too. Okay, 5 degrees a second stereo constraint. Okay. Now is that in here? It is not. So we're going to want to Zoro's personal. Merge that in. Curvature factor learner. Get cherry pick. There's no reason not to run this, literally. Once done testing, get pull again and compare before and after heat. In fact, if you just wanted to pull again, for see changes. Can't believe that wasn't in there. If you're using a steer actuator delay 1.0, you want to make sure you have proper constraints in your MPC. And in fact, you kind of want proper constraints in your MPC period, because well, constraints are important. The MPC doesn't need to generate angles that are a billion degrees a second. It makes no sense. Encato toolkit. Installation on Windows. CYG win. Yuck. I have Linux on my other partition, but I'm booted into Windows right now. CYG win. Fuck it. CYG win. Install from the internet for all users. Local package directory. Choose a site. Mirror service. Okay, that's not bad. Oh, I didn't. Yeah. Select a same download directory. Fuck. Yeah, install from the internet. Oh, okay, CYG, okay. It says that we need select packages, Devel graphics, and X11. What is this shit? Package all? Oh, Jesus. Bin utils. Okay. CMake. Why is this in parentheses? It's stupid. GCC4. Oh. Oh, that's great. So since we don't know, oh, I can't select. That's bullshit. Fuck that. I'll just do it later. Because what I want to do is I want to change the control horizon to like 10, because NPC control horizon. Jesus Christ. There's some charts. Alright, fuck that. Prediction control horizon. So, the control horizon number of MB moves calculated at control interval k. Control interval k. That falls between 1 and prediction horizon. The default is 2. Regardless of your choice for M, which is M, when the controller operates, optimize and move at the beginning of the horizon is used, any others are discarded. Small m means fewer variables to compute in QP at each control interval. If the plant includes delays, some AV moves on affect any of the plant outputs for the end of prediction horizon, leading to singular QP, whatever. Please use the review command. Small m promotes does not guarantee a internally stable controller. So I wonder if they mean delay as in terms of seconds or minutes, or if they mean like delay like a few hundred milliseconds. I have an idea. A MATLAB adaptive NPC.
In this video, additional MPMX. In a previous video, we discussed that adaptive link model and start angle value. You can download, accept that.
Okay, there's the adaptive NPC. Their control horizon is 3. Their prediction horizon is 10, and their control horizon is 3.
In the order that we've
Come on. So this is where the model parameters come into effect. So center from mass, distance from the wheelbase to center of mass. You got your tire stiffness values. You have your mass, and I think this is rotational inertia. IZ. I could be wrong. Come on. Alright, prediction horizon 10, control horizon 3. So what is the prediction horizon? Control horizon. We don't know what the prediction horizon is. So Ocado. Ocado. Jesus Christ. No. Integrations with continuous output use a prototype in the order MATLAB of the paper you refer to. Control horizons. Auto-generating microsecond solvers for nonlinear MPC, Ocado integrators. Okay. You can use a non-coincident grid. Define a certain integration step size on the solver. Take different number of steps and shoot interval described in the book. In the book chapter. Okay. In actual code, you can do this by providing a vector of length equal to the number of shooting intervals, and the vector specifies how many integration steps you want to take at each interval. In C code, this would look like this. Which num steps D matrix num steps. Where's num steps defined? Num steps. Speed num steps, step size 0.1. 0.15. Oversampling. Let's just look at crane. Look at the crane example. Num steps 5. Num of integrator steps. Integration steps. QP iterations. All right, number of integration steps. So what's the difference between an integrator step and this is not exploited in that. Okay, whatever. Let's look at the control horizon. See what pisses me off. So we have the control horizon is a constant integer of 50, right? And then you have 1 times control horizon, which is hilarious. Plane power. But yeah, if you want to know how to use something, you take a line of code, you stick it in GitHub, and then you find examples of people using it. So model predictive control. Autonomous vehicle for lane tracking, obstacle avoidance with a Kato toolkit. If you take a look at this PDF, it shows you the car kinematic model. So we have yaw, velocity, steering wheel angle, longitudinal acceleration. He has some input constraints here. Well, actually, we'll save this for later. And if you take a look, he actually has obstacles on the course for the NPC. So it misses the obstacles, which is hilarious. Pretty cool. Actually, I asked him. It's fucking MATLAB, man. Yuck. Um, Python bindings for Ocado. That's cool. Okay, car example. Multi-objective car. Problem transferring a car from initial position to specified target, minimum time with the minimum control effort. So initial position to target, drive 200 meters while minimizing control effort, accelerating traveling time. So this is more like navigating a car. Excuse me. NBC controller real-time vehicle ultimate control. Oh, Berkeley has a thing for it. So that's probably why everyone is what is this? Planning just M. Fucking MATLAB, man. Okay, Harmon memory enhanced predictive control. Car. Memory enhanced predictive control. Control system auto control. Warm started by an estimator. Whoa, neural network estimator. That's cool. On a car model. Ah. I think they wrote a paper about it. Using memory of motion to efficiently warm start a nonlinear predictive controller. That's cool. More shit that isn't documented. Okay, CG. So anyway, we want to take a look at something called the control horizon. Open pilot 3. That's funny. Update on April 1st. Let's call the hubs up pilot 3.5. I have a feeling, yep, comma open pilot generator. Let's see. Well, let's see here. This might not. DDF. Yep. So that's yeah. Huh, it's Shane. Hi, Shane. It's like the only user avocado is wait, comma is the #1 user avocado, which is hilarious. NPC simple, okay. One species can out of 2 states. So anyway, the control horizon. Still haven't answered the question of what the whatever horizon was. But anyway, I've recompiled by changing the control horizon before, and it didn't result in any different code at all. So that's kind of dumb. What we were doing? Okay, so we were enabling PID stereo cost 1 for the Prius. We were doing speed-based tuning. This 80 miles an hour, 0.6. So we'll keep the KF there. We'll take a look at. We can't take a look at that. Maybe SSH. What? PowerShell has PowerShell is native SSH client. That's crazy. CD data open pilot. Python. Yes. We'll take a look at the curvature learner. We will import pickle. We will actually. Oh, how the fuck can you paste? That's that stupid fucking Windows thing. Oh, there we go. So those are my persisted curvature values. That's a Python shell, idiot. See, data, get curve, debug. Oh, CSH is laggy. Wow, that's a big ass file. So we're gonna do rmuser.tar misc cd data shit c data open pilot get pull no get reset hard. What is my camera offset? Wait, what am I committing this to personal? That's why I've been hugging. Camera offset value. Zero personal pull. No, I get reset hard. Oh, because that's why. Okay. Camera offset. Get reset hard. Get pull. Okay. Camera offset value. We'll go ahead and reboot. That's why. Because that's why you don't want to do a get reset on a branch that people pull from, because they'll be in hell trying to. They got to do the get reset thing to fix it. So. That's why you do the revert thing. So that's booted. And I do have my 5°2 stereo constraint in here. What is OCP set nod? Number of online data. Whoop-de-freaking do. There's 17 there, and there's actually 17 here. I've counted before. I wonder why the first 5 time steps are 0.05 seconds, and then it's 0.15 after. Why do they have a non-uniform time grid? Non-uniform prediction horizon. .ch. Czech Republic? Alright, God, what, blah, 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 non-uniform prediction horizon. Uniform. Go away. Prediction and computational burden. Uniform relatively reduced computational burden, the cost of smoothing performance. At the cost of smoothing performance. Adding weights to cost terms can improve the performance of unit weights to cost terms. Non-uniform step length. What the fuck is that? Size of the optimization problem grows quickly with increased steps. Prediction horizon computational burden become very heavy. Move. Okay, we're not using move blocking. Variable forecast resolutions. We're not using variable forecast resolutions. Oh, it's my cat. Go away! Go away! You could be climbing on the electronics, man. You're a good cat. Just go away. Oh my god. 5 minutes, 5 plus scene, 5 minutes, 1 hour. So, simulation results. Fluctuations of power. So we're using a non-uniform time grid because we don't want Ocado to use as much CPU. So that's at the reduced. That's at reduced smoothness. Oh fuck me. Well, I want to go for a drive, so I'm gonna stop the stream. Bye. Do you want to log out? Yeah.